Alright, I put my sound on, so you guys should be able to hear me now. We'll get started in about one more minute. Alright, we got 22 people here, and there should be 28 in the class, so that means some people are not here. If you know if people are not here, I am going to try to upload these videos. They can be reviewed on Twitch itself. I did start a YouTube channel as well for our videos, so that is the link to the first one. So if you know people who are not here, you can share them that link to yesterday's lesson. I'll try to do this each day, so you could always view the older ones, because I think on Twitch they do get deleted after a week. That way they're on YouTube forever, so you guys can just see them. And I'm curious, if you have not received the new packet, either from the school or if it wasn't delivered to you, could you just let me know? You can just throw it in chat. Just let me know if you haven't gotten it, because by the sounds of it, it sounds like everyone has it. Alright, so I guess everyone has it. Alright, that's good. That means we can progress past parallelograms and possibly into the properties of the rectangle. We are going to practice a little bit of what we did yesterday, just to familiarize ourselves with some of the parallelogram proofs, especially these new types of proofs in the coordinate plane. You should have received graph paper in that packet, so you guys can now graph along with me if you'd like to. There should be 4 pieces. They are front and back, so there should be plenty of graph paper for the remainder of this unit. And you can also probably squeeze 2 or 3 graphs on a single side of graph paper. But that should be all the general announcements. I did give us everything from this unit. And again, there's even the homework pages in there, but if you remember from yesterday, I'm not actually assigning them. They are just for your supplemental practice. I will always be on the stream a little bit earlier, especially if you have any questions about that practice. That way I can answer those questions and help you out if anyone chooses to do that practice. But we're going to jump into right what we were doing yesterday. We're going to just kind of practice one of these examples on our own and to see kind of what we can do. I'm going to, for now, ignore the directions and exactly what it says. It does say determine whether the figure is a parallelogram using slope formula. I'm just going to change that into prove it's not a parallelogram. And we're going to find that this is not a parallelogram as soon as we graph it. I think this is the first time we're actually proving something is not something as well, which is common. The Regents can ask this. I've seen it infrequently, not too often. Amber is asking if it is unmuted. Can you guys hear me, or is it just Amber? Okay. I'll give her a second. Okay. Amber, try refreshing the page if you're on a desktop or a... Actually, she can't hear me. Tell her to refresh the page. while Amber tries to get her sound going, we can proceed to graph these 4 points on our graph paper. So while she's figuring that out, let's start graphing this. That's a good question. What formula do we use? Because we used both yesterday, I'm going to let you choose whichever one you want. Remember, I've changed the direction, so you don't need to use slope. I've just changed it to prove it's not a parallelogram, so you may use either formula, whether it's slope or distance. Because in the future, you're always going to have that option to use whatever formula you want. So that is a very good question. I will let you know right now, based on what we kind of discussed yesterday, that I will be using slope myself because I think slope is easier. You could always use your rise over run after you graph it. I think there's a lot of benefits to using slope over distance. But again, that is your choice. If you're someone who likes distance, go for it. So I'm going to start graphing these. So we have W is -7, -4. -7. There we go. W. -6. So there's y. So one of our coordinates does go to -13, so make sure you make your graph a little bit bigger. I made mine a little small. And then z is 1, -12. Alright, and this is the shape that we get. And different from yesterday, obviously, because remember what we're trying to do. We're trying to prove it's not a parallelogram. So the fact that it doesn't look like a parallelogram, it shouldn't be a surprise at this point. And if you're trying to prove it's not a parallelogram, you only need to choose the two sides, either the two sides that don't look congruent or the two sides that don't look parallel. So since I'm using slope, and I look at these two sides that I'm highlighting right here, these look parallel. So if I'm using slope, I probably don't want to choose these two sides because it might come out that they are the same. But I think the other two sides look probably not parallel. So I'm going to do the slope to these. If you're using distance, it looks like you could choose any pairs of sides. As long as if you're doing distance or slope, make sure you choose a pair of opposite sides. Don't choose two adjacent sides because that doesn't prove what we want. Or in this case, disprove it. So I'm going to go ahead and do my slope formula. Remember, we're going to use our subscripts. So since I'm going to be finding the slope of these, I'm going to be finding the slope of WZ. So I write a little WZ with that slope variable. I'm going to set that equal to change in Y over change in X. So WZ. So I'm going to highlight them. W, Z, -12 minus -4 over 1 minus negative 7. We have the double negative, so we're going to switch that to a positive. We get negative 8 over positive 8. And we get a slope of negative 1. And just by looking at the graph, I think we could have made that conclusion. Again, you could do your rise over run. We know these slopes should have been negative to begin with. It does look like it's going down 1, over 1, down 1, over 1, down 1, over 1, and just following that pattern. So a slope of negative 1 looks good. Now we have to check the slope to x, y. And unlike yesterday, we are not predicting the same slope. If it was the same slope, then it'd be parallel. We're trying to disprove it's a parallelogram. You don't always have to show the graph. I think I mentioned yesterday that the Regents will word it as the use of the graph is optional. I don't like when they say that. I think everyone should graph it, but if we're being, super technical, you don't need to graph it. The benefits of graphing it is you probably don't need to show the math for slope if you graph it. If you don't graph it, you have to show the slope formula. So there's a benefit of graphing it. Can't we find slope without the graph? Yes, we can. That's the benefit of graphing it. So technically, you do not need to be showing this work. I always will, though, because I will always show my work. But technically, if you graph it, you do not need to show this work. If it's distance, you have to show the work no matter what, because you can't count distance. That's kind of the benefits of graphing it versus not graphing it. So those are all really good questions. But I always just kind of like to double check myself and whatnot. I'm going to do xy. Negative 13 minus negative 6 divided by 5 minus 1. I'm going to switch that to addition. And we get negative 7 over 4, which is just that. It's negative 7 over 4. That doesn't actually reduce to anything. Then we're going to bracket this off. And kind of like we were doing yesterday, we wrote either not congruent or not parallel. We wrote congruent or parallel. Now we're going to write not parallel. And just like an ordinary proof like we were doing yesterday, we do need a statement that is going to justify our proof. You do not need to show the other two sides, because once one pair of sides is not parallel, it cannot be a parallelogram, because the namesake of a parallelogram is both pairs of sides are parallel. Once we have found one that isn't, we are done, and we can justify that quadrilateral WXYZ is not a parallelogram, since opposite sides are not parallel. If you use distance, you would have to find two different numbers, and then you would just have to change, instead of parallel, you'd have to be congruent. It's okay if we do it in a different order. Yes, so negative 6 minus negative 13. Yes, that order would be fine, Julia, if you went in that order, as long as you are being consistent. You technically can call y1, y2, really whatever you want, as long as one coordinate is the first one, the other coordinate is the second one. And that is how we would disprove something. So disproving something it's really the same thing as a regular proof. I suppose it's even easier because you only have to do one pair of sides rather than two. We're going to be doing this with every new parallelogram we do up at this point. So we've really only done the parallelogram. We're going to learn 3 more parallelograms, which is the rectangle, the rhombus, and the square. And the proofs are going to be a little bit longer than this one. This is as easy as it can get. And we'll see how to do them when we cover each of those parallelograms. But as far as this packet goes, we've done 3, we've done 4. I'm not going to do 5 or 6 with us unless you guys feel relatively comfortable with this so far. Like I said, we're going to do plenty more of this once we do the other parallelograms. There is a homework page. Again, it's not required. You can just do it for practice. You know to use parallel or congruent if, depending on the formula you're using. If you're using slope, slope tells me if 2 sides are parallel. If you're using distance, which would find the length of the sides, then you would be using congruent. That is how you're going to determine if you're using parallel or congruent. If you always use slope formula, you will always be using parallel, and you'll never need to use congruency. So with that, you guys can now take out, I think this is the first page of the packet that I printed out for you guys, which would be the properties of a rectangle. So I'll give you a second to kind of take that out. This is kind of the new packet. We're just going to go over the properties of the rectangle, which are pretty straightforward, but one other thing that we will kind of cover. There's another page in your packet. It's probably near the end. It looks like this. This is going to be, you're going to see me reference this page quite a bit. This is kind of just a reference page on all the different parallelograms we are going to talk about, and it's a nice little flow chart that shows us that, you know, all rectangles, which we're about to cover today, all rectangles are going to have all the properties of a parallelogram. Because a rectangle is a parallelogram. You could call all rectangles parallelograms, but not the other way around. Not all parallelograms are going to be rectangles. So in order for a rectangle to exist, it must first be a parallelogram and must have the properties of a parallelogram before you can go on to the rectangle. So you'll see me reference this sheet a lot. It wouldn't be a bad idea to just have it out. This flowchart is going to be especially important when we do proofs, both coordinate geometry proofs and regular statement reason proofs. This will be really nice. And that's why if you look at the notes on rectangles, it says right at the top, rectangles have the same properties of parallelograms, and all 5 of them are written out. And if you're trying to prove that something is a rectangle, you must first prove it's a parallelogram. I'm going to write that little note to the side that in order to prove something is a rectangle, you must first prove it's a parallelogram. This is going to be true with all of the shapes. What packet is the flowchart? It's not in a packet. It's just a single sheet. It's probably towards the end. I don't exactly remember where that flowchart was, but it should be in the packet. Okay, good. And that's why that flowchart is set up. That's why the parallelogram is at the top. If you want to prove any of the other parallelograms, meaning the rhombus, the rectangle, and the square, you always have to do this step first. And how do you prove something is a parallelogram? You're going to use any one of these 5 properties. And we've already done 2 of them, which is usually going to be the main 2 that we're going to do. Opposite sides are congruent or opposite sides are parallel. We should remember that you need to only show one of these, and then the other four would be true. Okay? Let's get into the actual properties of the rectangle. One of the important, one of the, glaring obvious differences between a parallelogram and a rectangle is the rectangle has those nice, sharp, 90-degree angles. So in a rectangle, all angles are 90 degrees. Now, one little note, sometimes if you look up a technical definition of the rectangle, it's a parallelogram with at least one right angle. Now, this definition might seem a little bit strange at first, because why does it say only one right angle rather than all four? If you look at the properties of the parallelogram, if one of the angles happens to be a right angle, well, that means the opposite angle is a 90-degree angle. And because the consecutive angles are also supplementary, the consequence is going to be that all four are going to be. And that's why it uses at least one right angle. Because you could see this in a multiple choice question. It might say a parallelogram with only one right angle. Well, that makes it a rectangle. So that's a good little note to keep in mind. The other property that is unique about the rectangle is going to be about its diagonals. The diagonals are still going to bisect each other, but in the rectangle, the diagonals will be congruent. All right, so those are going to be the main properties that we will kind of work with. And we have these examples down here. I don't plan on doing all of these. These are, in my opinion, very straightforward, very easy. So I'll probably do one with sides, one with angles. And then I might jump to some of the algebra ones. And then we'll see where we go from there. And then we can maybe cover the rhombus. All right. So let's just take a look at number one. I'm going to do 1 and 3. So for each, it says each quadrilateral is a rectangle, and we're just going to find the missing measures. I'm just going to fill in everything in the diagram like I usually do, and then we'll go from there. So first and foremost is, well, just like a parallelogram, opposite sides are going to be congruent. But then we are going to need to figure out the diagonals, and there's nothing labeled in the diagonal. They don't give me any additional information, but this is the fact that the right angle is going to be really useful. So if I actually highlight, it should become obvious how we can find the length of one of these diagonals. It's going to be Pythagorean theorem. So let's apply Pythagorean theorem. We're going to find the length of the diagonal, and the diagonal in this case is the hypotenuse. So why don't you guys do that? All right. So I'm just going to do Pythagorean theorem quickly on my calculator. You should get 676 for QS squared. And then we just got to square root that. And we get 26. Which makes sense. The diagonals, since it is the hypotenuse of the right triangle, should be more. And if that is 26, we can still assume that, well, diagonals are being bisected, so we could label these as 13 each. And because we don't need to do Pythagorean theorem again, because both diagonals are congruent, which makes all 4 of these pieces right here congruent, which is going to be 13 and 13. And if you look a little bit further, kind of at all the little triangles that make up this rectangle, these triangles right here that I just highlighted, since both sides are 13, that does make it an isosceles triangle, as well as the other two. There's a lot of symmetry involved with kind of the rectangle. All right, and then we can just fill in our answers right over here like we usually do. You get 10, SR is 24, SQ, which is 26, PR, also, oh sorry, SQ, yeah, SQ is 26, and then PR is also 26, right? Yeah, and then QT, which is 13. So pretty straightforward. Just be aware that, Pythagorean theorem can still come into play. All that triangle stuff could come into play. If you can find a triangle in any shape, especially if that's a right triangle, it wouldn't surprise me that if they gave you one of the angles, they could make this into a SOHCAHTOA problem real easily, just by giving you some of the angle measures instead. So all your triangle theorems could come into play. Let's take a look at number 3. Where definitely some of those triangles are going to come into play. So we can utilize that fact about isosceles triangles, like I just mentioned. If all of these are congruent, we're going to have a bunch of angles which are going to just be congruent because of these isosceles triangles here and here. And we could prove that the triangle right underneath it is a congruent triangle quite easily, side angle side, because vertical angles are congruent here and here. So that means this angle and this angle, all 4 of these angles are exactly the same, and one of them is labeled as 27. That makes them all 27 degrees. If those are all 27 degrees, right where that N is, we can figure out all of those angles because it's just a triangle. And all 3 angles must add up to 180 degrees. So 27 plus 27, I'm going to subtract that from 180. And I get 126. And then we can find the information from the other 2 triangles. You have a variety of ways you can figure this out as well. You can take the supplement. You have linear pairs here. You could even take the complement because on these edges, we know these are all 90 degrees. And you're going to have the same properties as before. These are 2 other isosceles triangles. They're all going to be the same measure. I'm just going to take the complement really quick. That's going to give us, so 90 minus 27. What's that? 53. All of these in here are going to be 53. And then we can find those last 2 vertical angles, really any method that you want. It's going to be, what is that, 54, I think? No, it can't be 54. Oh, this is 63, isn't it? My apologies. These are 63. That makes a lot more sense. That would make this 54 then. And then we have all the angles labeled in the diagram. Once you got them all labeled, then we can start filling in these blanks right here. So MJK, that's just a 90-degree angle. MJL, 63. JLK, another 63. KML, 27. And MNL, which is 126. So those are really the two different ways we could utilize a rectangle in terms of angles or sides. So I'm not going to practice any of these other ones. Feel free to practice it on your own. I'll be on early tomorrow if you want to see answers to them, if you would like to practice it on your own. I'm going to flip over and we will jump to some of the ones that include some algebra. So I will jump first to number 8, which gives us Jm is x plus 17. Let's see, where's Jm? So that's right here. So I'm going to label it in there, x plus 17. And then mk, which is this one right here. And most of you probably could see the relationship between these two, that this is 5x plus 17. Obviously, the yellow line is longer than the blue one. But utilizing the fact that diagonals are congruent, and the fact that they bisect each other, you can justify the fact that the blue one is exactly half the length. So you have two options here. You could take the expression, the 5x minus 23, you could divide it by 2, which immediately I don't necessarily like because these are odd numbers. And if you divide them by 2, you are going to be either working with fractions or decimals. The other option is you could double the length of Jm. And we could set that equal to 5x minus 23. So I like that option better. So I'm going to take x plus 17, and we're going to double it. Just make sure you put it in parentheses, because you do need to double both numbers, just like usual when we double an expression. That is what we can set equal to 5x minus 23. Distribute. You get 2x plus 34 equals 5x minus 23. I have HK oh, Julia's right. Oh yeah, that changes the entire problem. So good catch. My apologies. Because it is MK. So I apologize. A lot of you are asking questions. You guys are right. I made the mistake. These need to be set equal to each other because these line segments are in fact congruent. I had HK incorrectly labeled. So using the fact that diagonals are congruent and bisecting each other, yes, we would just set these equal to each other. We wouldn't double anything. So this is a case where we just take 5x minus 23. Set it equal to x plus 17. So, subtract x, add 23, and then divide both sides by 4. So we should get x is equal to 10. The question does say, find JL. So in this case, JL is the entire line segment. So that is something we need to consider right there. When we plug x back in, you should be able to plug in for either one because you should get the same value. I'm going to plug in for x plus 17 because I think that's far easier. And you should get 27. But just realize when you get 27, for plugging in 10, that's half the line segment. The other one is 27, making JL 54. We'll do one more. We'll do one with angles. So we'll take a look at... we'll do a more challenging one. Let's look at number 13. So obviously, the thing we need to do is figure out how these two expressions are related to each other because they are in different locations. So you have a number of options. And when it comes to a rectangle, if they give you one angle, you can likely figure out every single angle. So the goal is, well, let's figure out exactly what this angle is. The one where the 5x plus 7 is labeled. We can figure out the actual measure to that angle. Then we could set it equal to that angle and then solve for x because that is the basis to this question. So we have the 134. I think the best way to get there is we're going to take the supplement and we're going to figure out the measure to this angle right here. So you can just subtract from 180. I believe that gives us 46. So if that's 46, remember if it's an isosceles triangle, due to the fact that it's a rectangle with congruent diagonals, so opposite angles are congruent, so the rest of the angles are distributed between there. So you can just subtract from 180 and then divide by 2. I'm going to do it right now, subtracting it from 180, divide by 2. Each angle is 67. Now that we know that that angle is 67, we know what we can set that 5x plus 7 equal to. So 5x plus 7 is equal to 67 degrees. Subtract 7 from both sides, and we get 5x equals 60 for a final answer of x is equal to 12. So not too challenging stuff, at least when it comes to the mathematics behind these geometric figures. Rectangles, not too bad. Tomorrow we will look into the rhombus. And then once we go over the properties of the rhombus, we're going to jump more into those coordinate geometry proofs using how are we going to prove a rectangle using coordinates, how are we going to prove a rhombus using coordinates, and then ultimately we'll jump into the square as well. But I think I'm going to end it right there. Again, there are quite a bit of people who are not here. If you know of anyone who's not here, tell them to just watch the old videos, or I will be posting them to YouTube. I'll be on for a while, so if you want to ask me questions, I'll be here. I got my physics class starting in 20 minutes, so if anyone wants to practice or anything like that. But we are done for the day. All right? Thank you, guys. Global? Is global going on right now? Okay. You're welcome, Olivia.